Okay, what I'm going to be talking about is the prospects for establishing a colony on small, frozen, icy dwarf planets. I'm going to talk about some of the challenges we would face and some of the possible solutions and why in the world we would want to go to a small, frozen, icy dwarf planet in the first place. Let's start quickly with brown dwarf stars. I guess everyone's familiar with brown dwarfs. They're essentially stars that were shortchanged in the mass department. They're not big enough to burn hydrogen. They do, for a little while, burn deuterium and, in some cases, lithium. So for the first few 100,000 years of their life, they actually look like a small M-class star. But when their fuel runs out, they stop producing energy and then slowly cool off. When they first fire up, their temperatures, again, similar to a small M-class star, 2,500 Kelvin. But as they cool off, we've found some brown dwarfs down to 400 Kelvin. They're not actually brown, they're more red. They radiate in the red, the infrared. And they all tend to be about the same size, in that of Jupiter. They're hard to detect, especially the older systems. There is one theory that Nemesis, if it exists, is indeed going to be a small brown dwarf, fairly cold. We've detected about 600 of these systems so far. And one estimate I came across said we have, 100 billion brown dwarfs in our galaxy, which compares favorably with the number of stars we have in the galaxy. So as we expand out, we're going to run into a lot of these things. They have accretion disk. So just like any other star, they're likely to have planets. But because they don't put out a lot of radiation, these planets are probably going to be, for the most part, small, frozen, icy dwarf planets. Orphan planets, I guess everyone's heard of the idea of orphan planets, rogue planets. We know now that planetary formation is a pretty dynamic process. A lot of planets, protoplanets, get thrown out in interstellar space. And if each star, as it forms systems, throws out a half dozen planets, there's a lot of these things floating out in interstellar space. So these are planets not bound to any host star. They range in size from Jupiter to Ceres. Estimated number, we have no idea. Brown dwarfs are hard to detect, but these things are almost impossible to detect. But a great number of them are probably going to be small, frozen, icy worlds that, we might want to take a close look at. So the colonization target that I'm going to propose is, small, frozen, icy dwarfs or Pluto-type worlds. They're lonely, frozen, but they have lots of volatiles. Lifeless, oddly enough, they do have the possibility of oceans, so we'll talk about that. They have a shallow gravity well, so it's easy to get on and off. In our Kuiper belt, and it may be that Kuiper belts are just an artifact of planetary formation. We have an estimated 70,000 objects, and again, one estimate I've come across said that there could be up to 200 Pluto-type planets in that Kuiper belt. We've, I think, detected, half dozen at this point, but we haven't looked very hard and very far at this point. And Kuiper belts, again, are probably fairly common around other stars. Now, I keep using the word small, but, understand, small is relative. Compared to, the Earth or Jupiter, Pluto is a very small world. But let's see, here we have Pluto, its moons Charon and Ceres sort of lined up to scale and, a backdrop against the U.S. So, they may be small, but that doesn't mean that they're not a complete world unto themselves. We know Pluto's diameter and mass fairly well. And we know that it's massive enough to pull itself into a spherical shape. Computer models indicate that if that happens, that you will get differentiation at least of the rocky material and the ice. The rock gravitates towards the center of the world, creates a rocky core, and the ice, floats on top of that, forms a mantle. Now, if we assume that the rocky core is roughly the density of Mars, then we can calculate how much ice we have here. And in this case, it turns out to be like 325 kilometers thick. That's a lot of ice. And if you calculate the volume, that's 3 times as much water as we have here on planet Earth. These things have been, floating around in, space for several billion years. They've accumulated dust and debris, so there's a crust on top of this icy core. We don't know if this crust is meters thick or kilometers thick, but, we expect it's there. And what is interesting is if the core is generating enough heat through radioactive decay, if the ice crust is providing enough insulation, we could actually have liquid oceans at the interface of the two. So if you're a writer looking for an interesting setting, this might be one to consider. Here's Charon. This is Pluto's moon. And again, same thing. We know its density. We know its density. We know its diameter. If we assume the rocky core is the same density as Mars, then 40% of Charon turns out to be ice, again with a crust, and again with a possible ocean. Here's Ceres, an asteroid, and I guess the current thinking is now that it's actually a Kuiper Belt object that has migrated in and is masquerading as a asteroid. But it comes from the Kuiper Belt, or there's reason to think it comes from the Kuiper Belt. And again, we know its mass and diameter fairly well, not as well as Pluto. And 20% of the mass of Ceres turns out to be ice. And that gives it a ice mantle about 100 kilometers thick. So when I say Pluto-type worlds, that's kind of what I'm looking at. They all seem to be variations on a theme, a mixture of rock and ice. The rock's got to be in the center. And what I'm proposing is that settlements on Pluto-type worlds could be beneficial. First of all, they seem to be very common. The old saying, "No matter where you go, there you are." Well, it looks like the galaxy is constructed in such a way that no matter where you go, there's going to be a Pluto-type world not too far away. So if we develop one skill set, one technology that allows us to establish a colony on, these kind of worlds, anywhere we go, we can probably find one, and we can set up a colony. Yeah, they exist around brown dwarfs and orphans. And one aspect I've always, struggled with is, say we build a colony ship and we send it out to a star, and there's no Earth 2 waiting for us. We're going to have to terraform a planet. That's going to take thousands of years. What do we do in the meantime? And I guess what I would suggest is that the colonists would find a Pluto-type world and set up shop, and we'll get into what the colony would look like, but it could be fairly comfortable for some period of time. It would be a good base to explore and exploit a new star system. And Pluto itself, again, would make a good dry run for an interstellar mission. Here, if we, can build a colony ship and we just have to run it up to 1/10 of 1% the speed of light, and Pluto is 40 weeks out. If we're going to go interstellar, we're probably looking at 10% the speed of light. This is a drawing by Robert Kennedy showing what a dome on a vacuum world would look like, and it shows city on one side and an agriculture center on the other. It's transparent. This is pretty much a standard of science fiction, but for a number of reasons that I don't have time to go into, they just really don't work. And let's see, we've touched on, or Jan touched on the idea of the effects of long-term health effects of weightlessness, microgravity, low gravity, Where's the cutoff? We're not really sure. These issues here, they're pretty well known, and she talked about the eyesight problems. Humans apparently do not do well if they are exposed to weightlessness or microgravity, and we don't know where the low gravity cutoff is. Is it, I think the suggestion was made, it was a quarter of a gravity, half gravity, unknown. We also have some unknown issues. They tried to hatch some foul eggs, I guess, on the International Space Station. It did not proceed normally, which raises a lot of significant questions with human reproduction. What kind of gravity do we need for the race to be able to reproduce itself? And again, that's very much an unknown question. We do know that children, as they grow up, need to run around in a one-gravity environment in order to develop strong bones and muscles. And what are some of the other long-term effects? So I think, if you're looking at building a starship, if you're looking at building a settlement, somehow you've got to address the need to provide one gravity for the colonist. Radiation exposure, again, we touched on that earlier. In the U.S., we allow radiation workers to receive 5 RIM a year. Think of RIM as sort of a measure of damage done to the body by radiation. We try to keep the general population down to 0.5 RIM, a tenth of that. Just background radiation that we all get is about 0.36 RIM per year. If you get medical x-rays, that number can actually be a lot higher. This is a NASA design study looking at space settlements. And they looked at the radiation exposure question and concluded that we needed 550 grams per square centimeter in order to reduce the radiation exposure to the occupants to 0.5 RIM a year. If you convert that into metal, that's 68 centimeters of steel. That's a lot of steel. And they addressed the question of relativistic heavy ions and said basically we don't really know how to deal with that question, and it certainly invites more research. Here, are some inputs, and given those inputs, again, assuming that the rocky core is the density of Mars, then we can calculate what the gravity field inside Pluto looks like. And it's kind of interesting that as you drill into the ice core, the gravity field actually goes up. And then you hit the rocky core, and then it's just pretty much what you would expect. But knowing the gravity density within Pluto, knowing the masses involved, we can calculate pressures at different depths. And this dog leg here is the interface of the rocky core and the ice mantle. And it turns out to be 33,000 psi in the case of Pluto. Our colonists are probably going to be operating in this area. This is the surface, and then this here is the depth we go to get into Pluto. So what is interesting is that if you go down 160 meters, in the case of Pluto, the weight of the material overhead is pressing down on you with a pressure of 1 atmosphere. So you see where I'm going with this? If we drill down 160 meters and carve out a cavern, and if we're dealing with ice, that's pretty easy. You just need a hot water heater, a pump, and a hose, and you can hollow out a cavern pretty easy. And if you're careful to keep the ceiling at the right depth, and then fill up the cavern with 1 atmosphere of pressure, the ceiling is completely supported by your 1 atmosphere of pressure. You have no limit on how big you can make this cavern. In fact, you could make the cavern as big as the world. Then we're getting into the shell world idea, but that's probably more than what we want to deal with right now. The surface of Pluto, and probably most worlds that we're looking at, 30, 40, 50 Kelvin, which is pretty cold. And if we want a shirt sleeve environment in our cavern, we're looking at probably 300 Kelvin. So we're going to need some pretty thick insulation. So we hollow out a cavern and we provide lots of insulation, on the ceiling, sides, floor, and that's what the red represents. Put in 1 atmosphere of pressure, which is what we're breathing right now, provide heat and light, and you've got yourself a shirt sleeve environment that you can walk around in that, could be fairly comfortable. Also, remember that number I asked you to keep in mind earlier, 250 grams per square centimeter is what we needed. And what we have in this case is 19,000 grams per square centimeter and over a distance of 160 meters. So there's a good chance we've pretty well addressed the radiation exposure question here. Now gravity is only 6 or 7% out of Earth. A 200-pound person running around is going to weigh 14 pounds. That might be kind of fun, but you're not addressing the issue we talked about earlier about people need 1 G in order to do well. This slide, if we want to grow plants, the whole point of this slide is we don't have to duplicate the solar constant. Plants are not very efficient with the light they use. Need to take a quick detour here. The Stanford Torus. This is a space settlement that was proposed, three decades ago. And basically what you do is you take a habitation tube that's 130 meters in diameter, and you fold it into a torus that's 1.8 kilometers in diameter itself. You spin it up to 1 RPM, and you've got, at that point, 1 G within that habitation tube. And again, the space settlement, people seem to think that 1 RPM is about as fast as you want to rotate a settlement, certainly for long-term purposes. Their design looked to house 10,000 people, but they had a lot of agriculture spaces in that. If we decide to dispense with that, we might be able to double that number. And the design's pretty well fleshed out. So look it up on the internet. It's out there. I got this slide from NASA Ames, and I want to thank them for it. It shows you what a Stanford Torus would look like, if it's in space and being constructed. What I would propose is we take this torus and we put it in one of our caverns that we've just completed. And shielding is provided by Pluto, so the radiation question goes away. 5, I thought this was going to be an 8 presentation. Shielding provided by Pluto. You're going to have to deal with the gravity, so supported on maglev rail system. And, you've got a nice 1G environment for people to live in. Again, this is a slide from NASA Ames showing the inside of a Stanford Torus. And, it's a pretty nice place to live. So our colonists would essentially live in this environment. They could, during the work shift, maybe leave and then go deal with the caverns. But then at the end of the shift, they come back. So they're living in a 1G environment most of the time. So the basic settlement configuration looks like a Stanford Torus in one of the caverns. Then we'll have a number of low grav spaces where we can, grow plants and maybe forest. That's where the manufacturing would go. You could have seas if you like seafood. Storage is no problem. You've got a world to use, and then connect all of this with the tubes, and you're pretty well shielded from radiation, and it's all a shirt sleeve environment. The material resources are actually not insignificant. If you mine the ice, you're not getting just H2O. From comets, we know that they exhaust water certainly, but also other ices such as CO2, ammonia, methane, and we've also observed these other chemicals. So just by mining ice, you're going to be able to get oxygen, carbon, nitrogen. Then you've got, I'd also predict that the icy mantle is going to be salty for reasons we won't go into. But then you've got the surface crust that you can mine, and that's probably got a fair number of silicates and metals in it. And again, the thing's been floating around for several billion years. It's probably bumped into asteroids and comets. And if you can mine those, your metal problem is solved. Energy, sunlight is not going to work, wind's not going to work, so you're looking at some kind of power plant in order to power your colony. And fusion is the logical one. Deuterium, if we could learn to fuse that, problem solved. We have 3 times as much deuterium on Pluto as we have here, so not an issue. Do we have helium-3, perhaps, that we could mine? Maybe. Something else. The Polywell people are making interesting claims. Waste heat, of course, would not be any problem here. Key technologies we're going to need. 2, my score's going down. Okay, we've talked about this before, cheap heavy lift to LEO, the ability to build large structures in space, and Robert talked about the fact that we have no idea how to do that yet. The ability to move large, starships, spaceships, fusion power plants, we've talked about that. Ice construction technology, I haven't talked much about that at all, but that would be a key technology we need to develop. Need an airtight, durable, highly efficient insulator for our caverns. Large rotating structures in a low gravity environment, that's that maglev system we talked about. Large bandwidth communications, and 3D printers. I think those would be real handy. So, the argument is basically that, we can form colonies, that would be pretty comfortable, long-lived on small, frozen, icy dwarf planets. Any questions?
So, a couple of quick points, really great presentation. First, we've heard of Bernal spheres, I presume?
Oh, yeah.
So, I don't say about this. Secondly, you talk about the interstellar probes and going to the planets and are we going to actually find somewhere. I think it's quite clear, looking at observational platforms and extrapolating them into the future, that we're going to know before we go. And we've actually done some studies in the Project Icarus study where we looked at that a little bit. And we can actually work out what the resolution of exoplanets are going to be in, say, 30 years from now. So we're going to know where we're going before we go there. The second point I want to make, which is a really fundamental one, is there's an assumption that the planet is the place you want to go to. And actually, if you look at the point that Gerard O'Neill was making with the O'Neill cylinders, was he was saying actually space affords us an enormous amount of volume compared to a planet. And so you want to live in space and on the resources of space. So if you've got a world ship and you take it to the stars, you don't necessarily want to live on the planet. You may want to stay on the world ship. And you're just using the local resources. So that's just another point to think about.
Yeah, but one of the, questions about the world ship or the O'Neill cylinder is it's sitting there in space, but you have to have resources to use and process.
Yeah.
And here, if you've got a whole world to provide material for you. So, yeah, floating around in space is nice, but again, you got shielding issues, that I don't think they're well addressed, and other concerns.
I'll connect in with video.
Okay.
While you're answering one more question.
Probably one more question, and just for all of our speakers, I've just been advised that there are people watching on Ustream. Yay. And we're getting comments back that the speakers need to repeat the questions from the audience because they're not hearing your questions. So when you're giving your answer to any questions, speak into the mic and try to at least paraphrase or restate what the question was before you answer. So last question for Ken, and then we'll go on to our next speaker.
Well, once again, from the point of view of SETI, I think this is very interesting. In the SETI community, there has been quite a bit of debate. Actually, there was a full conference once at the SETI Institute about dwarfs and all that as good locations for extraterrestrial civilization. I don't think that they considered rogue planets at the time, but after I heard your points, I would add that topic. So the bottom line is, perhaps you might consider submitting some abstract for future conferences. There will be one in 2014 in Toronto. If you like, you would be appreciated, I think.
Well, good. Thank you for that comment.